So, ladies and gentlemen, thank you very much, Elena, for such a kind of introduction. And I'm not able really to live up to this wonderful introduction you gave me. So, what will I speak about? Well, when I was invited to make this talk, I thought I should speak about what I know about, which is eutrophication and coastal lagoons. And then I thought, no, I'm not going to speak about what I know about. I'm going to try to give a panorama of water and coastal management through the ages. So, this is a risky decision because there are lots of experts on different aspects of water and coastal management in this room who know far more about the topics that I will just touch on. So my apologies to you if I misrepresent your area of speciality. So I also chose to look and seek for examples that were relevant to the students and the alumni of water and coastal management over the years, to also show respect to their cultures and the long history of water management and coastal management all over the world. So humans have been managing their water resources for millennia, and there are lots and lots of fantastic examples, and I apologize if you're not represented in this list, but I did try to choose some that were relevant to our alumni. So I'll start with Mesopotamia. This means the land between two rivers. And of course, the land between two rivers is a wonderful place to have lots of water and to develop agriculture. There's good evidence that this is where agriculture was developed. But it's also a place that's precarious because, of course, you're vulnerable to floods and biblical floods and mythical floods. So this is the flood tablet about the Epic of Gilgamesh, which I'm sorry to say is in the British Museum. Sorry about that. But obviously, it's in their mythology all those years ago. It was definitely a problem. Floods were a problem. So they had probably some of the first hydraulic engineers in order to control these floods using a system of levees. They had canals and dikes, and they were mainly to control the floods, but they were also to irrigate. And parts of this system are still in use. But what's really amazing about this is that they had laws and regulations about the maintenance of these channels and the maintenance of these levees and dikes. So right at the beginning of water management, these people realized that the governance was really an important aspect as well. Of course, the Egyptians practiced basin irrigation also, and they used the natural rise and fall of the River Nile. And they also constructed these networks of earthen banks, and some of them were parallel to the river. They had different orientations and different size basins. But this made them a really productive land because, of course, the alluvial soils were very rich. No need for fertilizer, much worse for eutrophication with fertilizer. They also monitored the rise and fall of the Nile. And they monitored using these nilometers, and this is one of the great nilometers, but there are many different types of nilometers. They also developed many irrigation tools, so in a way they were also hydraulic engineers. And some of the tools were very simple, but simple is not always not good. Simple can be very good. And here is one still in use in Portugal. Of course, the Chinese should definitely figure in this. And I have to tell you that this is one of the best science books I've ever read, so I'm plugging this book. It was written by Philip Ball, who was an editor for Nature for many years, and it's a wonderful book about water management in China through the ages. And the first figure, the great Yu who controlled the waters, he predates all the written records in China, and China developed writing very early on. They had two aims, like in Mesopotamia, to provide irrigation, but also to defend against floods. And they did engineering at an astonishing level, and they carry on doing engineering at an astonishing level, and we'll see that through this lecture. This is the Grand Canal. It was started in 486 before the Common Era, so 500 years before year zero. And it's 1,800 kilometers long. Obviously, it took several centuries to build, but it certainly started very early on. And they also invented the lock. I was trying to find what the word for lock was in Italian and in Spanish. I only know it in English and French. But it's a system so that a boat can go up a river when there's different levels. So the Chinese were certainly very early water managers in many ways. And of course, the Romans. The Romans. They had professional water managers. These guys did all these calculations using that weird Roman number system, you know, that's always the bit that confuses me. The Romans did so many great things, but their number system was really very difficult to use. So how did they do all those calculations? Anyway, they designed, they built, and they maintained the Roman water system. And the Romans really liked their water. They were very clean people, and they liked to have their baths. And even if they didn't have a bathroom in their house, they had public baths. So by 250 of the Common Era, there were 11 aqueducts delivering water to 1 million Roman citizens. And so they were very, very good water managers and engineers. This is the Augustan Aqueduct in Bologna, and it brought potable water from the river Seta to Bologna. And this is the one in Cadiz. In Cadiz, the aqueduct is 83 kilometers long. It's one of the longest in the Iberian Peninsula and one of the largest in the Roman world. I learned a lot when I was preparing this lecture. And it brings water from far away, a long way from Cadiz, for instance, from the springs of Tempul. And it was probably set up by Cornelius Balbus Minor. In Portugal, we also have Roman aqueducts, but we thought they were such a good idea that we carried on building them through the Middle Ages and right through to the Renaissance. But the original aqueducts in Portugal are Roman aqueducts. And this is the one near Coimbra, the top right one is the one near Coimbra, which is the best Roman ruins in Portugal. Now, the Romans also liked to get rid of the dirty water. They had toilets, they had sewers, which we did not have in London in the 1700s. So these guys really knew their wastewater management as well. They had, these are public toilets of the 2nd century. And this is a sewer, a Roman sewer. And this, I thought, this must be a great book to have in your bathroom. the archaeology and sanitation of Roman Italy, toilets, sewers, and water systems. I really enjoyed it online, but I'm actually going to get a copy because I want to have it in my bathroom. They also understood about water storage. This is the Roman water storage system in Constantinople, now Istanbul. It's a massive system. I've had the privilege of going there and visiting it. Be careful, it's very slippery. But it's a wonderful building in itself. It's like a cathedral inside, like a water cathedral. It's really a beautiful building. I still have a cistern at home because I'm not linked up to the water distribution system. So I harvest rainwater and keep it in we call it cisterna as well. So thank you, the Romans, for that. The Colombians. So this is the river basin that David studied for his master. And it's the Zenu people from the Magdalena River basin. And they also had these perpendicular channels to the rivers. And the channels were to manage the river floods and channel them into an area that was low-lying. So, because they understood also about topsoil being washed away. So it would then be gathered in this area, so then they could use that soil and later on for their agriculture. And they built their dwellings on the ridges between these channels. And the Arabs, well, all agriculture, even when I was a child, which is kind of a long time ago now, in Portugal, was still using the Arab system. They were fantastic. So this is one of the great water wheels of the world in Syria, and we've had some wonderful Syrian alumni in this project, and also a water wheel in Morocco. And I noticed there are other Spanish people in the room. Can you tell me what you call these in Spanish? Is it Nora? Noria. Okay, I wondered because in Portuguese it's Nora, and I thought maybe Nora Martinez, like Norias because of her name. So in Portugal, they're called Noras, and they were still in use when I was a child. I remember them very clearly. If you drive near the airport in Faro, near where our university is, you'll see a whole series of them. And they were operated by donkey, or if you were rich, ox power. And they used the animal to move the wheel that brought up this chain of buckets of water. Now the Mexicans, they should also be acknowledged. Again, a land on the edge of the water. The Mexicans, their capital was linked to a group of 5 connected lakes. Now, I've only labeled 2 here. The main one was here, and this is where they had their capital. But remember this one because I'll come back to it later on in the lecture. And they built their capital on 2 islands, which they extended using Chinampa. Sorry if I mispronounced that, Esther. And these are small artificial islands. And they had causeways and dikes to connect the islands to the mainland. And I'll come back to this other lake in a minute. So now let's have a look at the past of coastal management. And again, I've covered, in this case, mainly European, sorry, the Egyptians, I know you're not European, but mainly European places. So one of the earliest mentions I found was this, of course, this, the mother of all lighthouses, the Pharos of Alexandria, that was built 3 centuries before year 0. And it lasted until year 1300, when it was destroyed, finally destroyed by an earthquake. So this was a building built to last. And of course, they knew how to build to last. Pyramids are still there. The Romans, again, built extensive salt works. The word salary comes from salt. And so salt has always been a very, very valuable commodity. This was the earliest one mentioned in a document, but obviously it was much earlier. It was mentioned in this document, but it was a much earlier construction. And obviously we see now already the sort of encroachment of humans on the salt marshes and on the wetlands. And there are many examples. Here's one close to Ravenna. Here's one close to Cadiz. And here's some in Portugal. Some of them are abandoned. A lot of them are abandoned now. But this one is a very productive one. It specializes in producing fleur de sel, and it's where one of our Wacoma students did her PhD. Again, you can see this is the Ria Formosa in Portugal. Just a little bit about lagoons. And you can see that they have cut off these areas for the salt, the water to evaporate and leave the salt behind. So they've definitely changed the hydrology of the lagoon doing that. Now, again, a Roman was the first to document what was going on in the Netherlands. In the Netherlands, Pliny the Elder described these wonderful Frisian coastal defenses, a system of dams, walls, and dikes. He was a naval and army commander, but he found them very notable. And first of all, they were just artificial hillocks of earth, but then they started using stone. This is a good book as well, Panorama of the History of Coastal Protection. And of course, Venice. I know it's a lagoon. So work has been going on, and you'll see this. I'll mention Venice several times through this lecture. Work has been going on since very early on in Venice. And there are all sorts of ways of building on the salt marsh and of protecting the embankments, and all sorts of technology was used. This is to drive the piles into the mud. Now, why have I included this one? You see the little heart here? This is where my grandfather lived. This is the town in north of England. We're talking here on the west coast of England, the best coast of England. This is the town where my family come from. And this road here is Lord Street. And when my mother was a little girl, it used to flood quite regularly. And this here is Banks. Banks was called Banks because they built banks to protect themselves from the tidal surge. And we're talking big tides. Most of the Europeans in this room are Mediterranean, so here we have 9-meter tides, extreme tides. And so they had to build seawalls. And all this land here has now been reclaimed. The coastline has a very, very gentle slope. So when the tide comes in, it comes in at the speed of a galloping horse. But the Dutch are the top changers of the coast in Europe. And they started very early on. They started in the 12th century, 11th, 12th century. And they were reclaiming, and they finally, in 1923, completely dammed this and formed a lake. So this is now freshwater lake. Now, in the 1800s, there was a lot of port expansion, and it was mainly because of the colonial empires. So there were important sea trade suddenly became really, really important. There were port works in the UK, in the Netherlands, in Belgium, in France, and in Spain, and this is the port of Cadiz. I know we're going to have a lecture about the port of Cadiz later on today. And I'd like you to just look at these. This here is the port of Ancona, close to close to us. And this here is the port of Cadiz. And what I want you to look at is that these are not natural shapes for a coastline. Coastal development is based on static structures that we build in nice straight lines. Nothing natural going on here. So this is really about man versus nature. It's about holding the line. And you can see what happens when you build these port structures. This is the estuary of the Guadiana. On this side is Portugal, and this side is Spain. And you can see that the sediment is accumulating here and eroding here. So sometimes what happens when you do this is that you interrupt the normal dynamic equilibrium of the coast, and you may move the problem to somewhere else on the coast. Another reading recommendation. This is about moving the problem to somewhere else on the coast. It's a novel, and it's definitely good holiday reading. In fact, if you look on the cover, it says, "The perfect book for the beach bag," from the Times Review. It's a good book, good read. I recommend it. So the Dutch, we go back to the Dutch again. In 1953, there was a terrible flood, terrible, perfect storm, the perfect storm in the North Sea. And many people died in Holland, but also on the bad side of England, the bad coast, near where Mike lives. And do you know how many people died, Mike? In this part, yes. So obviously, as a response to this, there was a decision taken to build these enormous tidal barriers. And so these are the delta works in the Netherlands. And in Britain, on the other side, they took a bit longer. This is the Thames Barrier that was first started in 1982. And Venice continued on their work. They consolidated jetties, they built more groins, they raised their quaysides. So these are examples of hard engineering, but during this course, I hope you've learned that they're not the only solutions. You also can have soft engineering techniques. And this supports natural processes. The idea is to restore the natural dynamism and to rely on natural elements such as dunes and vegetation. And I know some of you did their master thesis on this. And there's also the whole field of eco-hydrology, which are also nature-based solutions for hydrology. So here we have an example of beach nourishment, but beach nourishment may require lots and lots of repeated applications. And here we have some examples of sand dune stabilization near Ilha Cristina in southern Spain, just quite close to the Portuguese border. And this is a situation where we have managed retreat. This is another adaptation, and it's possibly what will happen to the system that José here studied for his master. Because this was a high-risk area called Surfer Point, and they had to just move everything back. They couldn't maintain the situation as it was. People were in danger. We also have the opposite approach, which is managed realignment. One is managed retreat. The other one's managed realignment. And managed realignment allows some flooding, but some controlled flooding. You don't repair your seawalls, so you save money there. You allow the sea to breach the defense. The flooded area becomes wetland. You have to compensate the farmers. I don't know how successful this has been. Mike, can you tell me? There's some very good references here about it. Kerry Turner and Tiziana have worked a lot on this. Has it been a great success? Yes. The bigger. So it's a local solution. Okay. Yes. Um, so is the other option setback lines? There's some lessons that we can learn from tsunamis. Um, this is a picture of a tsunami aftermath in Hilo in Hawaii. Now, Hawaii is right in the middle of Pacific, so it can get hit from tsunamis, from earthquakes from every direction. And they have very frequent tsunamis because of this in Hawaii. But I'm going to draw your attention to these two, the one in 1946 and the one in 1960. So the Hilo tsunami actually came from Alaska. The earthquake was in Alaska. But it generated a big tsunami, and there were nearly 160 deaths in Hawaii, but only 6 in Alaska. And the waves in Hawaii were about between 10 and 18 meters. So that's quite a big wave, even for a top surfer. And then there was one in 1960 as well. Oh, they rebuilt. After the tsunami, they rebuilt in the same place. And then they had another tsunami in 1960. And this was generated by a very big earthquake in Chile. So, as I said, the earthquakes can be a long way away. And there were 61 deaths in Hilo. Lots of homes were destroyed, and also some very big waves. So after this, they decided, well, maybe we should set back. If we reconstruct, well, we shouldn't reconstruct so close to the shore. And so the setback lines for reconstruction, they used the area flooded by the 1960 tsunami in order to decide where the setback lines should be. So now I'm going to talk about, so that's enough about the past. How did I decide past and present? So year 2000, this millennium, that's how I decided. So I'm just going to touch on a few different places around the world as well. Dams. Dam the dams. They interrupt the flux of water, they interrupt the flux of sediments, and they interrupt the flux of nutrients. They actually cause erosion at the coast, and they really cause a lot of problems. But of course, dams also solutions to a lot of problems of water management, controlling floods, keeping reserves of water. So there are plus and minus to every dam issue. And of course, our friends the Chinese, they like very big dams. But, I don't know why this one's here. Okay, I do know. So this is one of my bee in the bonnet. It's in the wrong place, but it's about desalination. It's about desalination. Is this really what we want to do? Why do we have to use the same quality water to brush our teeth and flush our toilets? This doesn't make sense. We have all these desalination facilities being built, especially in Saudi Arabia, Israel, and the United Arab Emirates. But there's lots also in Europe, so in Spain and Malta. Soon we're going to have one in the Algarve. But in the Algarve, we've got, I think, 41 golf courses now, and we're planting vast avocado plantations. And avocado is a very thirsty plant. It doesn't make sense at all. Now looking at coastal management. This is the Venice Moses project, and I'm sure you who are in Bologna, you probably went to see it, never mind learn about it. And so I won't go on very much about it, but it's closing off. I know it's a lagoon. 3 mouths, 3 inlets, and the flaps that come up. They lie down on the seabed, and then they come up in order to protect the lagoon when there's a tidal surge, acqua alta. This is a type of beach nourishment in the Netherlands, again. The sand motor, which is, I was trying to work out how much 21.5 million cubic meters of sand would look like. It's an enormous amount of sand, I decided. And some solutions as well for the Baltic, again, lagoons, sorry about that. These are floating rafts. Miguel Ignacio, who gave you some lectures about ecosystem services, worked on this project. And I'd like to point out that the Mexicans were doing this a long time ago. And you remember that other lake? These are the floating gardens in Xocomilco. So now let's look at the future, because that's what you're going to be handling. You're the future of water and coastal management. So flood hazard mapping. So this map of Shanghai, this shows the 250-year, 500-year, and 1,000-year flooding hazards. But let's not forget that Shanghai is a sinking delta, and that the sea level is rising, and that we think that actually the severity of some of the flooding may be worse in the future. So these flooding maps need to be in the context of climate change. They have a very good system now for informing the public of an oncoming cyclone, and also of the level of the flooding. They also have that in Venice, of course. Another dam, and we have an Ethiopian in the room, I believe. That's why I put this one in. It's the Grand Ethiopian Renaissance Dam. It's caused a lot of controversy with the countries downstream. Egypt is obviously not very happy about this, but they've dammed the Nile historically as well. And this is one of the biggest inland lakes, artificial lakes in Europe. It's the Alqueva Dam in Portugal. And just recently, sorry about the quality of this picture, is from a newspaper article. They've started putting these floating solar devices on the surface of the water to generate electricity. It says hydroelectricity, but also solar energy. But there's a lot of push now to remove some of these dams. And this is an NGO about dam removal in Europe. And they've mapped all the dams, and the ones that marked in yellow are their success stories where the dam's been removed. But we need water. This is a picture of the Po a few weeks ago. And this is a picture of the reservoirs in southern Portugal, really serious water shortage. So why do we have all these golf courses and avocado plantations? The Chinese also have a problem. They have a problem with the Yellow River, which is running almost dry now. And so they need to transfer water from south to north. And their project was enormous, started in 2003. And there are 3 main routes, the western route, the middle route, and the eastern route. They also instigated their sponge cities policy. It was in response to some terrible flooding in the early year 2000s, and it became an urban policy in 2014, and by 2015 it was started in 16 cities and then another 13 cities. And a lot of it is based on principles of ecohydrology. The future is now also for coastal management. So after we saw what happened with the Banda Aceh earthquake and resulting tsunami, there became far more interest in actually giving some good information to the public about tsunami warning. So here's an SMS warning system for tsunamis, but also some good, I think this is Indonesian. Wint, can you confirm that? And however, there are many different types of tsunami warning signs. It doesn't seem to be uniform. Another response in the Netherlands are these floating houses. So instead of damming, you just build your houses to float. And also plans for floating cities in the Maldives, again as a response to sea level rise. But why are we making problems for ourselves? I mean, this doesn't make sense. You know, these people have a problem and they're trying to solve it. These people have a problem they're trying to solve, but these people are creating a problem for themselves. Thank you very much for your patience. I hope that I didn't do injustice to the place you came from. Thank you. And I'd like to acknowledge Future Earth Coast for the continued support they gave throughout this whole program, and the vice chairs here. So thank you, Future Earth Coast, for all the support over the years. Bye-bye.
Thank you, Alice. You, of course, you met my presentation since you have always been an inspiring person, and also the PowerPoint was in line with this, raising informations, inviting us to look back to build our future. So thank you very much. I think maybe students made already many questions to you, so I don't know if there is one questions, or maybe also we have time to speak with Alice later on, and we move on the next. I appreciated very much. I think we all appreciated very much the contribution of Alice Newton to our knowledge, to our program. So thank you again. And then I invite on the stage an expert of climate change. And probably he started, Professor Antonio Navarra. He is a new person acquired by our department, actually, but he has a full life dedicated to climate change, even when the climate change was just thought to be so far. And he is actually the president of the Euro-Mediterranean Center for Climate Change. As I said, is now professor has been acquired as professor of my department. So it's a pleasure that I have to have Antonio here and speak to the Wacoma audience and all the hosts we have, persons we have present here. Thank you, Antonio, for coming.
Thank you. Oh my God, what's happening? Thank you for the invitation. I understand there is something wrong on that side of the room because everybody's on this side, so I don't know what's happening on that side. So I understand. I'll try to stay away from it because clearly something is going on there. So good afternoon. I'll try to basically lead you through a brief journey in these 3 hours that I have. I think, Elena, is that correct? Oh, it's not 3 hours? Oh, I'm sorry then. It was a little bit challenging because basically I'm not really an expert either on water or coastal. So the question is what kind of story I'm going to tell you this afternoon. So I'll try to, I patched up something together. So let's see what came out of it. And I like to start from the issue that, you know, climate is something that we all know what it is. But the question is, what about if you try to do a scientific consideration of climate? How do you do that? So that's interesting. You probably have an aunt that says that there are no mid-seasons anymore. Everybody has. In Italy, it's true. There's never been any mid-season, by the way. So the question is, how we can treat it scientifically. And I'd like to start from this picture that does move. Likes to end. It doesn't go forward. Okay, we made it. Okay, I'd like to start from this picture. This is the Everest on a typical day in the summer. Now, if the Everest is this crowded, this gives you an idea of what we're doing to our planet. So if we crowded the Everest this much, it's clear that we have acquired a capacity of changing the real structure, the fabric of our planet. That's what we're doing. So we have acquired this new dangerous capacity that is of changing the structure, the composition, in a way, the real stage on which we're acting. And I think that's is a new capacity. Mankind has always modify the environment in which they were living, but this is the first time that we have a global capacity. And so I think we have to start from here, and we have to try to understand how we do, how we deal with this problem. And the issue is that once we realize that climate is something that is dynamically interacting with us, then we suddenly understand and realize that is a component in a multitude of area, sectors, and human activities, including, of course, the coasts. And I would like to start from here. These are the equation of climate. I always show them. In case some of you find the solution, please contact me immediately. I would appreciate that very much. So it's an interesting story. We knew the equation. This is not a science where we have to discover the equation. We knew the equation. Unfortunately, we couldn't solve them. They're very complicated. So this basically made our science a descriptive science, and we made it into a quantitative science only when we were able to actually perform experiments, and experiments can be done if we are able to manipulate this equation and find solutions. And the trick was to exchange the mathematical complexity of these objects with an enormous number of elementary operations. So that was the trick. That's what gave place to the modern numerical models. So now we can actually solve this equation. We can make experiments. We can take, that science make experiments. I would like to, people that were saying they don't like dams, I would like to dam Gibraltar and see if the Mediterranean really dries up 2 meters per year, as our calculation says, or not. That would be a wonderful experiment. But they don't let me do it. They don't give me money, and they don't give me the permission to do it, unfortunately. So how do you do that? Well, I can make a model, and actually I can close Gibraltar in the model, and I can do many more exciting things. And this idea started from this group of people in Princeton, where they devised this technique in which you can take this complex system, and then you can solve them numerically if you have somebody that is doing calculation fast enough. In this case, an electronic computer. And now we get to our problem. This is the symbol. This is the Wall Street index of our effect on the planet. This is a picture you have seen millions of times. This is a concentration of carbon dioxide in the atmosphere from 1960 on. And this is, I would say, as I said, the symbol of our impact on the planet. And we can use those models to actually try to understand how these changes affect the real planet. And we need the model because, you know, the units on the y-axis are part per million. So we're dealing with really small number. And what we see here is an increase of a very small number. So even if the increase is spectacular, people will use words like exponential, explosion, whatever, it's still a very small number at the end of the story. So in order to evaluate if the complex feedbacks in the climate system are in the end amplifying this signal or not, the only way you can do it is by using a model. You cannot do it by eye or by, you know, waving your hands or using very clever theory. You cannot do it, period. So models have become these really important tools in which we understand how this modification, that in a way are subtle. So we are modifying a very minor component of the atmosphere, but that minor component, once gets into the grinder of the feedbacks of the system, turns out to have some amazing impacts. And of course, what you do is that you discretize the equation, so you create these grids that are progressively finer and finer, and then you can get to, you know, we started with blocks that were 500 kilometers 30 years ago, and now we are down to 30 kilometers, and progressively you can see feature appearing. And the early model didn't have the Mediterranean, for instance, or UK was not there. And then, you know, slowly feature emerge, and you start to get a more and more detailed picture of what the impacts of the increasing carbon dioxide is on our climate. And that's where the situation is now. This is a typical model. In this case, it's a forecast model. What you see here are not satellite pictures. This is the model representation of the movement of the accumulated precipitation. So you can see it's pretty realistic. Now, the interesting thing is that this is impacting with our system. So if the physical system by itself is complicated, once we put the human component into that, well, that's a nightmare, right? Because what's happening is that we change the carbon dioxide changes temperature, precipitation, for instance, that impacts via a number of effects on agriculture, for instance, or human settlements, or economics, the emissions, and then you go back to square one. So we have added another major uncertain feedback to the system, and that's why we like to discuss, to refer to this as the human climate system. Unfortunately, we had another equation. If I could, I would like to add another equation in those equations that's called humankind, that has impacts on the rest. We are not at that stage yet, but we will get there. And there is a machinery in which we can do this. We can even localize the information even more, starting from these global climate models. We can use finer models that localize information until we reach the scale in which they can be introduced in impact models that are specialized to particular application, including, for instance, dam modeling or reservoir modeling, and that's where my expertise stops. And we can do the same with the ocean. And this is an example of a global forecast of the ocean. That we actually, this one, we do it at CMCC. And we do this every day, and this is about 5 kilometers global. And as you can see, the forecast goes into high detail, and we can reach down, and we provide this information. Now, is this enough? No, it's not enough for many coastal applications, and we need to do more. And actually, but you can use this information to actually provide the necessary large-scale information to drive specific models, and then can be used for impact studies, for instance. Scenario can be made with these large-scale models, then you can use the information, and then you drive specialized high-resolution model like this one, for instance, and then you can see the impact, for instance, of infrastructure, of planning, of policy, of deployment of NBS. And you can actually make a statement about what would be the impact of this measure. So these becoming tools for the analysis of policy, of choices, advices, as people say, inform policies and devise strategies that sometimes is easier said than done. And you can do even more. Oops. Go. Move. Okay. Models can become highly specialized. This is a case that we did in the Savannah River in Georgia. The colors are the domain of the models. We can actually simulate all the way down to 1 meter resolution as you get into the river system. You can do what people now call urban oceanography. And these models can be used, for instance, for forecasts of sea level as hurricanes are climbing up the coast. And using the unstructured grids that are used here, using this technology, we can have really detailed and successful forecasts of complex geography. Or you can do this one. This is a case that we did for Dubai. This actually is the palm over there. And this is another case in which a high-resolution structure model, and you can see it gets into the channel, into the city, in which these models can be used for impact. Oops, what's happening? This is the Taranto system that we've already seen. And this is one that we have made in Otranto with the same resolution. So this technology allows you to connect what is happening offshore with what is happening along the coast, inshore, in a way the transition coastal zone is connected smoothly between the offshore ocean and even the riverine system inland. And the objective is to create a smooth system, a seamless system in which all these components allow you to describe the physics and the ecosystem of the coast, because all these models can be provided with ecosystem models in a proper way. So, going towards a conclusion, a conceptual point. All this is showing that we actually modified the scientific paradigm as we have known it in school or in the last 500 years. Probably people have taught you that there is theory and experiments, and scientists do a little bit of that, a little bit of that, in order to make sure that they're not wrong. Well, we're adding something more. We're adding simulation. And simulation is something different. It's a theoretical construct because it has nothing to do with the real world. But it's somewhat an experiment because we cannot predict what is coming out from a simulation experiment before you do it. So you can test hypotheses with simulation. So for the first time in 500 years or so, we have modified the scientific paradigm. And I think this is going to become more and more clear over the next decade as digital methods, computation, and data analysis will fuse in a single discipline. But if you want to have fun, you can actually try this game. This is free. It's on both shops, on Apple and Android. We have devised this simple game in which you're trying to create an economy on a planet and try not to go completely south because of climate change. So you have to manage emissions and economy and making your citizen happy. Otherwise, they will revolt, and then you have a problem. All this and much more, you can find it on our website. The website is at CMCC. This is the center where we are doing all this. That is basically an integrated center where we are studying the problem of climate change from the design of the numerical models, all this chain of models that I've shown you. We have many models. All the way from there to the definition of the impacts in many sectors, including the agriculture, ecosystem, carbon cycles, and so on, and all the way to the economic models and policy analysis and choices. So go there. It's going to be very informative. Thank you.
Thank you very much, Antonio. And I don't know, I'm a biologist, but I would listen to your presentations for hours because you have been very clear and also inspiring. Maybe it's the first time you meet Antonio Navarra, so maybe you may have questions. I see you in front. Maybe, or others. if you have any questions or if you need some time to think about, then maybe Antonio can stay for until the break, the coffee break. But any question at the moment? Anyway, it's okay. We go further, so we don't don't run out of time. I thank you very much.
Okay.
And yeah. So I lost my. Sorry, was concentrated on Antonio's speech, and then I forgot. And then, oh, Irene Delgado Fernandez, is she around?
Hi, I'm here online.
Oh, sorry. Yeah, sure. And then, yes, and thank you very much for being able to participate to our meeting. So online, we have many many issues going on, and thank you for the availability to speak online. And then she is again a scientist from the University of Cadiz. It's a pleasure to have you here. And then I leave you the microphone, and thank you very much again for participating to our meeting.
Okay, so thank you. Hopefully you'll all be able to hear me. Apologies, I cannot be there today. I tested positive for COVID a few days ago, and unfortunately my throat is not amazing, but hopefully we will go through this well. So I'm gonna share my screen, and please, hopefully that will be visible. If it is not, please, one of the technicians, you can just let me know. But I'm gonna continue, assuming that you can see it. And okay, so I thought that I would talk about coastal management from the perspective of beaches and dunes, especially from the perspective of beach dune systems as a physical system. So. As you said, I'm Irene Delgado Fernandez, and I'm currently working at the University of Cadiz. But before Cadiz, I worked in England for 10 years, in Ireland for 2. I did my PhD in Canada. I've been in Australia, and I've had a very long tour, and now I'm here talking to you, and it's a pleasure. So this is the outline of the presentation. I'm going to start by the big question: why is it important to study coasts? There have been several people before me talking to you about coastlines, so I'm gonna go quickly through the first few slides. I'm going to talk to you about the problem from a physical geography perspective and some of the solutions. And then I'm going to go into the nitty-gritty: coastal processes and beach dune dynamics, and coastal processes, beach dune dynamics, and people. And then I've got a few questions for you and some concluding remarks. So the big picture first, as you all know, Earth is a coastal planet. We've got over 1.5 million kilometers of coastlines around the world. That's like going around the equator 400 times. With 84% of all countries in the world having a coastline, so great variety of forms, climates, etc. And in general, we people are attracted by coasts, especially sandy coasts. And sometimes one wonders if we are attracted perhaps too much. You've got a typical image, well, not that typical, but an image here of a section of the coastline. The back beach and the dunes are all gone. You've got plenty of engineering, and then obviously, all sorts of the devices as well on the beach. And all these interacts with coastal processes and modifies our coastal environments. So that has implications for coastal evolution, and sometimes it has implications for unbalanced benefits. Who benefits from these constructions at the coast? So Why is it important to study them? I'm sure you've seen this already, but just as a very quick review, 40% of the world's population is living very near to the coast. The majority of our world's top mega cities are coastal, and coastal populations expand faster than those inland. They have a larger growth. And the problem is that currently we're seeing at least 70% of the world's coastlines eroding. EU static sea level is rising, and it will continue to do so. And despite predictions, there's a diversity of predictions, but just to give you an idea, in some parts of the world, like in some sections of the United States coastline, NOAA recommends, their latest recommendations from January 2017, is for planning purposes to use a sea level rise scenario that is extreme, and that is about 2 meters. We also have changes in the frequency and magnitude of storm events, and well, just to summarize this, basically, coastlines are an environment where most people on Earth are settling, which are eroding and exposed to flooding by rising sea level. So a little bit of a recipe for having to think about this. The problem is coastal erosion from a physical geography perspective. Again, I'm not going to talk about other dimensions of this problem. And when you've got coastal erosion, especially if it's in areas where people live, you've got loss of ecosystems, livelihoods, pollution, etc. In some areas, this problem of coastal erosion is very, very severe. And I'm just going to show you the Semarang coastline. This is in the north coast of the Isle of Java. That is 2002. This is a typical Google Earth image. And just to give you an idea of scale, this is a town here, and this is a trained channel. And these are, I'm guessing, I haven't been to this location, but I'm guessing these are people, say, fields for planting, agricultural fields. Well, that's 2002, this is 2008, and that is 2017. So obviously, well, you've got people needing to move, the loss of livelihoods, etc. In some areas of the world, this process is ongoing and it's severe. You don't have to go all the way, to the Isle of Java. We've got the examples of these in another places. This is Le Signal in France. In the 1960s, they built a hotel. It was 200 meters from the shoreline in the dune field, and then nowadays is the building is exposed to again ongoing coastal erosion. The recent case of the Collaroy Beach in Sydney, Australia, where they have taken a very controversial decision of installing a seawall, probably one of the last things you want to do, but again, another example of coastal erosion. And then you've probably seen this, but Cape Hatteras in National Sea. Oh, I don't know if you can hear all that noise. Sorry, I'm just going to stop talking for a second. There you go. Hopefully you'll be able to hear me, but the Cape Hatteras in National Seashore in the United States, this is one of the latest buildings being washed away by the seas. These buildings were built in the past with the protection afforded by large coastal dunes, and then the coastal dunes are gone, and this is what you get. And just out of curiosity, the building was sold relatively recent in 2020 for $275,000 US. So I'm going to leave it in there and allow you to make your own conclusions. Some of the solutions, there's a diversity of them. Some of the solutions are actually problems on their own, but I don't have a lot of time to talk about this. But I just wanted to tell you that usually you've got this hard engineering paradigm versus a soft engineering one. Hard engineering, I'm going to put the example of Japan. Japan is famous for having their coastlines cast on stone, and it's because 40% of their coastline is engineered somehow. So their solution to coastal erosion has been, protection in the form of engineering, seawall groins, the whole range. Versus soft engineering, which is mostly about, you probably already know this, but mostly about building beaches, restoring marshes, etc. Again, I don't have a lot of time to talk about this, so I'm going to continue. One of the countries that probably knows most about coastal engineering is the Netherlands. And in there, they're switching from, again, traditional hard engineering into doing these things. You probably know this. This is the sun motor. And off the coast of Poland, and they've injected millions of cubic meters of sand in there, and they're allowing the winds and the waves to distribute the sand along the coast. So this triggers a question. Why beaches and coastal dunes? Beaches and coastal dunes are being used now as an engineering strategy all around the world to protect coastlines against the flooding and erosion. And the reason for that, I'm going to show you the reason for that in a second, but the reason for that, the main reason, is because there's plenty of evidence, extensive evidence pointing to these type of nature-based solutions, with coastal dunes and beaches being one of the most efficient mechanisms against coastal hazards. So these are some of the images coming from Superstorm Sandy in New Jersey in the US in 2013. Got loads of imagery from this event. In the areas with no dunes, there was widespread coastal damage, but the areas with dunes quickly recovered after Superstorm Sandy, and there was limited damage to properties. So I'm going to move on, but just so you know, there's plenty of evidence suggesting that these are indeed good strategies. So I'm going to move into sort of the nitty-gritty, the main part of the talk, and I'm gonna talk to you about coastal processes and beach dune dynamics. And I'm gonna start by the local scale. Apologies for the relatively bad diagram, but what you're seeing here is the typical cross-shore profile of a beach dune system with a submerged area, the beach, the embryo dune, and then the fore dune. In the wintertime, with big waves, the beach is eroded. The sand that is carved from the dunes and the embryo dune goes all the way to the submerged area, and it's deposited in the form of a nearshore bar. And then during the summer, the gentle waves will push the sediment back onto the beach, and the embryo dune and the fore dune will grow back again. That is in a neutral to positive sediment budget scenario. So when you go to the beach in the summer, you'd expect to see a little bit of an embryo dune, plenty of sand on the beach. When you go in the winter, you'd expect to see maybe a little bit of dune scarping a flat beach, and then the sediment below the water where we can't see it, but it's there in the form of a nearshore bar. So that's at the local scale. At the regional scale, again, apologies for the bad diagram, but at the regional scale, beach dune systems are part of littoral cells or networks of sediment sources and sinks that build the coast. So sediment coming off cliffs is entrained by the sediment drift. Sediment coming off rivers is entrained by the sediment drift, and then it all ends up somewhere down the coast in the form of beaches and dunes, which are, after all, depositional coastal environments. It's a little bit more of the sort of sediment coming in and out of the littoral system, but that's a little bit the story. It's a bit the yard part of the network of sediment sources and sinks. Just an example of the Holderness Coast, which is maybe you've seen this today as well, but this is off the east coast in England. And the Holderness Coast is very famous because it's got very high erosion rates. So you've got bluffs there, cliffs made of unconsolidated material that erode very quickly. And they do what cliffs are supposed to do. They erode. Cliffs are erosional features by definition. They're trying to stop erosion, but in reality, from a natural perspective, the sand that comes off the Hornsea cliffs of the Holderness Coast actually joins some of the sediment brought by the Humber, and it ends up, forming massive barriers and beach dune systems a little bit down the coast in the North Pole, in the North Pole coastline. So again, this is a system that is linked by currents, etc. And at a transregional scale, coastal dunes and beaches are also part of larger transregional systems that are connected by coastal currents. So what I want to say with all this, just to close this, this first view on these systems is that beaches and dunes are border environments. They have unique characteristics, but they are not isolated. They are part of larger systems that play an important role in exchange of materials and organisms between marine and continental environments. So I'm going to move on to coastal processes and beach dune dynamics, and I'm going to add people now, see how people affect all these. And I'm going to start by the transregional scale now. So at the transregional scale, how do we humans affect this system? And I've chosen I've chosen three things. There are more than these, but I've chosen three things. Obviously, oceans are warming, the currents are changing, sea levels are rising, and the frequency and magnitude of storms is changing. And again, I don't have time to talk about the implications of all this, so I'm going to focus on the frequency and magnitude of storms at this transregional scale. And for this, I'm just going to select one paper, Webster et al., 2005, Science. And apologies for the bad diagram again, but you have time in the x-axis and the number of hurricanes in category in the y-axis. And the category 1 are this blue line, and category 3 and 2 are that green line. And as you can see, they haven't really changed that much. Yeah, it oscillated a little bit in category 2 and 3, but they haven't changed that much with time, okay, from the 1970s. This is to the early 2000s. But the red line, which are category 4 and 5, which are the big ones, these are hurricanes, have increased. And in fact, they're double. Not only that, but I'm going to show you some recent and extraordinary and exceptional events. 2005 was the longest hurricane season on record. We had Katrina there in 2005. Almost 2,000 people dead, millions of US dollars lost. We had 5 other large hurricanes that year, Dennis, Emily, Katrina, Rita, Wilma, and many other small hurricanes. 2013, simultaneous hurricanes. So by the time we were having Ingrid, Manuel was also affecting the coast. 2013, the year of the super typhoon in the Philippines, 13 million people affected. 2015, the strongest hurricane ever recorded in historical times, with 345 kilometers per hour wind speeds, category 5, and even they thought about category 6. And only 13 people died, because by then they had already learned how to evacuate the majority of the population. But a lot of expenses in terms of properties, etc. 2015, simultaneous typhoons. 2017, continuous hurricanes, Harvey, Katia, Irma, Jose, and recently we're having this idea of lost hurricanes. This is the typical spaghetti map of areas in the world affected by hurricanes and typhoons. And as you can see, by the time we were having Katrina in the States, it was sort of like that spaghetti there off the coast of Brazil. We had our own hurricane off the west coast of Europe as well in 2017, Ophelia. I don't know if you remember, category 3. So we're starting to see some of these big storms in areas of the world that one wouldn't expect them. And that has implications for how beaches and dunes react and for coastal processes. I'm going to go again down into, so from the transregional now into the regional. Beaches and dunes, again, are part of literal cells, networks of sediment sources and sinks. So the question here is, how do we, people, interfere with this network of sediment sources and sinks? So what about if we put a groin off the coast? We just simply interfere with sediment drifts and coastal currents. And that has an input that has an effect in the form of the decreased sediment, or the amount of sediment that goes along the coast decreases. You have a decrease in sediment input to beaches and dunes. We do this all the time. The Mediterranean coastline of Spain and many other countries, for example, is full of these things. Harbors and groins that just stick off the coast and will basically trap sediment on the upstream coast, and then the downstream coast is starved of sediment. It doesn't get enough sediment for beaches and dunes to grow and develop, and you have coastal erosion. We can also stop or slow down cliff erosion by putting seawalls, stabilization structures, and again, that means less sediment going into the littoral drift and less sediment going into beaches and dunes. We can put dams in rivers, slow down sediment input by, preventing sediment from reaching the coastline, and again, that decreases sediment input to beaches and dunes and triggers problems of coastal erosion. And we finally can enhance sediment output from beaches and dunes, literally by mining them, just bringing the bulldozers and taking the sand out. And the sand doesn't go too far away, usually stuck in the form of buildings. That is where most of the sand, most of the concrete around the world is based on sand coming off coastal areas. So much that some of these things have been actually really well quantified. So you have a UNEP and Petuzzi et al. 2014. You've got other quantifications. I've just chosen this one, but we said that the sand and gravel used for construction around the world equals the total sediment discharge of all rivers worldwide. It just gives you an idea of how much sediment we actually actively take away from coastal areas. And that the total sediment discharge of all rivers worldwide has been reduced dramatically, and that is because of dams. Okay, so I'm going to go down into the local scale now, and how do we affect the dynamic nature of the beaches and dunes at this local scale to the point that we can trigger coastal erosion problems. And again, if you remember, during big storms, sediment is eroded from the embryo dune and dunes. The waves flatten the beach, and then the nearshore bar will grow. This flat beach and this nearshore bar is now a protective strategy. It's a self-defense mechanism. It breaks the waves and it reduces coastal erosion. It reduces further dune erosion, basically. It's like a self-defense mechanism of the coast. And then in the summertime, again, when the waves are not too big, they're small swell waves, they will bring the sediment back onto the beach, and then the dunes will rebuild the dune area. Sorry, the wind will rebuild, brings the sediment back onto the beach, and then the wind will rebuild the dune area. But what happens if precisely when the embryo dunes are growing and the foredune is growing, when the vegetation is growing, which is in the summer season, what happens when you bring thousands of people into the back beach? Trampling will destroy the plants, and without plants, there's no binding effect, meaning the wind can blow the sand, but the sand won't stop in the dune area. Usually will go into the lee side and sometimes into the roads and buildings that is behind. Okay, so people, instead of vegetation, will have an effect for how dunes grow. And if you don't have strong coastal dunes growing in the summer, it is very likely that then erosion in the winter will be more severe. Or you can just have buildings in many locations around the world. As you know, we haven't respected coastal dunes to the point that the buildings are on top of the dunes themselves. And that has broken the dynamic nature and the relationship between the back beach and the dunes. So buildings instead of dunes. So having said that, I think I'm getting there. I just have a couple of more minutes. But having said that, I've got a number of questions for you, and I thought that for asking you these questions, obviously I'm not going to be able to interact with you from there, but I thought I would show you some of the images we've got. This is a wonderful book. It's called The Lost Paradises, and it's by Juan Pedro Bator. He's a Spanish photographer, and it dates to 2009. And I just want to show you some examples, and then instead of asking you, unfortunately I can't, again, interact with you there, but maybe you can start thinking about some of the mistakes that might have been made in these locations that could have triggered coastal erosion or that are now a problem for coastal management in the context of climate change and sea level rise. So this was Marbella, a small town, the Andalusian coast in Spain, 1961. And that is Marbella in Malaga right now in the 2000s. Okay, so you can see all sorts of engineering, etc., and you can see how developed the place is now. This is La Manga del Mar Menor. This was a massive barrier system off the coast of Murcia as well in Spain, 1963. You see that typical Posidonia deposits in there, sorry. And then that is La Manga del Mar Menor in the 2000s. This is the Remolinos, again in Malaga, in the coast of Andalusia. This was a small town, probably relatively easy to relocate a number of years ago. But now it is, well, it's not something easy to relocate, one would say. This is Punta Umbría in Huelva, 1961, and this is how it looks like now in the 2000s. Okay, so these are scenarios that are, at the very least, complex in the context of sea level rise and climate change, in the form of, increased storminess, etc. So, to conclude, coasts operate at a range of spatial temporal scales. They are at the intersection of marine, aerial, terrestrial processes, and they have a large diversity. They are subject to human uses and abuses, both directly and indirectly, increasing coastal populations, occupation of coastal dunes and back beaches, etc. And this has implications, in turn, for human populations, because people are exposed to storms and rising sea levels now. Coastal management approaches are facing a paradigm change in many countries with a new look into nature-based solutions and the creation of coastal dunes, etc. And I'll leave you there with two quotes. One is by Orin Pelkey, who says that the most expensive global coastal engineering effort is largely to save buildings, not to save beaches. So basically, the most efforts are now being put into saving properties, not natural spaces, and that the environmental and economic costs to hold the shoreline will increase exponentially in the next 50 years as it becomes more and more difficult to defeat nature. So I'm going to leave it in there because I don't have any more time. I had a final thing to tell you about the role of education in transdisciplinary science in all this and how important it is to communicate all these challenges to the general public. But I don't have time, so I'll leave it in there, and I'll be happy to get any questions you may have.
Thank you very much, Irene, for your rich but also very lively presentation with a lot of passion and, well, also perfect timing. Although you at the end you said that you didn't have enough time and you had certainly many suggestions to give us. Yeah, we're kind of well, we are used to this kind of interaction, but it's not the best. It's not the one we like. I wish you, well, to recover soon. At the moment, if you have any question, we are able. Okay, Victor, please. So, yeah, here is.
So can you
Victor Almeida, one of our students, now graduate students of Wacoma.
Yeah, Victor Almeida, alumni of University of Bologna. I would just like to ask you one question. You mentioned quite a little bit, let's say, about the climate change and how it affects human population. Do you see how these climate changes can affect let's say, it can be a cause for human migration? So how you explain the hurricanes and how you explain the house floating away, and in your conclusion, you said it has implications to human population. Do you see this affecting human migration? And if so, I just want your opinion on how you can explain a little bit how climate change and these disasters that are becoming more frequent can affect the human population and the human migration, per se.
Yes, thank you, Victor. Yeah, totally. I wish we could expand on some of those things because, yeah, for example, take the case of the Semarang coastline in the north coast of Java. I don't know. I don't know the numbers, but obviously those people are losing their livelihoods, and they're losing the fields, the cultivation fields, and the water is up to their houses. They put flooding of their roads. So yeah, those are what we now call, I don't know if that's correct terminology, but those would be, climate refugees. So yeah, definitely. In my own, maybe I'm more sensitive towards the problem is in countries that they don't necessarily have the resources to deal with the coastal flooding and coastal erosion. Because some other countries do have them, and the problem, I think, is that sometimes the solutions against coastal erosion and coastal flooding are coming from countries who can actually afford to put, big walls or to nourish their beaches and their dunes. This is examples like the Netherlands. The Netherlands spends a huge amount. Probably some of you know. I don't know the number, but a huge amount of their GDP is spent on coastal protection. Off the east coast of the United States, well, the beaches, I don't know the percent of the natural beaches there, but the majority of the coastline is nourished with billions of US dollars going into nourishment plans. So for the moment, they're keeping the shoreline in place because rich owners keep the shoreline in place via plugging in nourishment programs that are very expensive. But those are no solutions for the rest of the big majority of the world. I don't know, to tell you the truth, how big the problem is worldwide in numbers. But gosh, I should have put it. I decided to take a diagram because I didn't have time. But I did have a diagram showing the increase of populations living in low-lying areas. And it's huge in continents such as Asia and Africa. So, again, you've got these ongoing processes with climate change, sea level rise, increasing storminess. No, storminess is not increasing everywhere in the planet, but the big storms in huge sections of the world affected by typhoons and hurricanes are increasing. And then storminess, normal storms are also increasing in other places. But what I mean is that yes, it's a big problem. It affects low-lying areas. In some places, it is very dramatic. It is just a matter of a decade, like in the case of the Semarang coast. People are displaced, and usually people who are displaced are the people who can't afford some form of coastal protection, either hard engineering and soft engineering. And it's people who lose everything. And yeah. Sorry, Victor, that's probably a very long answer for telling you something that you probably already know. Sorry about that. We probably need another talk.
Yeah, no, great. Once again, great presentation. I enjoyed every second of it. This is more or less my topic, so I'll make sure to get your contact information from Professor Safabri.
Please do, absolutely.
Of course, and once again, great presentation. Thank you so much.
Thank you, Victor.
Yeah, thank you. We all thank you, yes, for the nice presentation. And thank you, Victor, for the question. It was a wide and difficult question. And we move on. And now I have the pleasure to introduce you one of our alumni in Stegen. So We have some of our alumni who will speak from now on. And Tegan is one of the first year student of this Wacoma 3, let's say. She comes from New Zealand, so really far. But now she got a PhD at the University of Padova. So for being an alumna, and also for being a scientist, we thought it was a pleasure for us to have Tegan here. So please.
All right, good afternoon, everyone. I guess first I have to apologize for those disappointed that I'm not Dottore Polette. You were stuck with me. So anyway, I'm going to be presenting remote sensing applied to coastal wetlands with 2 lagoon case studies. These are, well, close to my heart. And as Elena said, I am a PhD student at the University of Padova. And my supervisors at the moment are Andrea De Paus and Sonia Silvestri, which you will know, and Marco Marani. Okay. So the outline of today will be first like the Wacoma experience in general, and then I will pass on to the case studies, of which we'll have an introduction in general, and then the Rio Formosa Lagoon and Venice Lagoon, and finally we'll end with conclusions. So straight into Wacoma experience. Well, so I'm from New Zealand. As you can see, it's a very long way. And if there was a way to go through the center of the earth, I would choose that. Why Wacoma? Wacoma, as soon as I read the course description, I knew that I was going to apply, and I'm very grateful to be selected. Thank you. I chose it because of the course content, the institutions. I'm from an island country that's on the Ring of Fire, so coastal water and coastal management is highly vital to us. What I was doing before, well, this may look threatening, but I'm not actually here for like a zombie attack. When I was doing my undergraduate, I was a civil and environmental engineer, and this is for geophysical testing. Previous to Wacoma, I also worked in stormwater engineering, geotechnical engineering, GIS, etc., etc. So, Wacoma, as you can see from these lovely people, it was a really wonderful experience. We learned so much. The mobility was fantastic. The course learning, like, it's hard to have words for this. And I also, all my friends and colleagues, like, thank you so much. And I also really wanted to acknowledge a certain colleague that hasn't been mentioned, Frappe, the Wacoma dog. So since Wacoma, what have I been doing? So at first, thanks to the University of Bologna, I had the honor of doing an internship with Sagres Mirisco in Portugal, where I was extracting mariculture data for satellites. I also had the University of Cadiz Premio Extraordinario. And after that, I did the Murray Foundation research project, which was also on operational tools with satellite for lagoons and shelf seas. And I managed to publish my Wacoma thesis in the Journal of Estuarine and Coastal Self-Sciences. And then finally, I ended up in Padova with my PhD. So moving on to more of the scientific aspect of this talk. All right, why should you care about salt marshes? So salt marshes are ecologically and socioeconomically highly valuable ecosystems. They're particularly for the ability for blue carbon sequestration is the focus of my talk. They are also degrading, as you have heard, like a lot of problems today, in the coastal zone due to the high concentration of pressures in that area. So the monitoring of evolution and these drivers of change is really vital for coastal management and climate change mitigation. The reason I'm focused on remote sensing of these coastal wetlands is because it can provide key information that's spatially explicit And they're very hard to monitor in situ at the great size they are, and also difficult because of all the mud and low profile. There are, however, always uncertainties in applying remote sensing, so there's a lot of work that needs to be done to relate parameters, key variables, and generally to develop a method that can be applied in coastal management easily. So the first case study I'm going to talk about was the focus of my Wacoma thesis. So this is the Rio Formosa. My study area was a bit nicely outlined in red. So we were studying the shoreline change over time of about 30 years of these salt marshes using open source satellite remote sensing. We chose open source satellite remote sensing because though it has some problems, like the old images are very low resolution and there's cross-sensor variability, they're also capable of like doing long time series so you can truly see change. And they're also free and they have global coverage. So as you can see there, it's quite a lot of good reasons to choose them. So I'm not going to go into complete detail into like the full study here because time is short. But basically, these are some of the key results. So what you can see there, the red is erosion and the blue is accretion. So the main erosion is actually occurring at the base opposite the inlet. And the graph at the bottom, just to interpret, is showing the erosion that was derived using aerial photography and the erosion derived using the satellite remote sensing. And you can see in these key areas, the accuracy between the two is actually very good. And now this one here is more about like the type of shoreline, so whether it's like a marsh detached beach or undervegetated tidal flat. And some of the key findings for this was that actually the accuracy of this method with the remote sensing is much higher in areas with unvegetated tidal flat. So if this is, enthralled you and you really want to explore in exhaustive detail about what all the methodology and the results for this research, you can find it here. This is the article. And I would like to also note that my co-authors and all these institutions made this possible. Now moving on to the second study. So as part of my PhD, I am focused on the Venice Lagoon, and the key focus of this one is more blue carbon sequestration. So the study site is here that I'm going to talk about today. This is the San Felice Lagoons that you would have heard about already in the Master's Defense. It's also this work is part of the NASS project that with America, and it's a joint effort. They're doing a similar thing in South Carolina. So the reason we're looking at the carbon sequestration still at these sites is that carbon sequestration is spatially variable, and there's like the factors that define this are not well defined. And generally, they don't account for the interconnectivity between blue carbon ecosystems, such as between the mangroves and the salt marshes and the seagrasses. So if you don't define this, you can't define the true value, and they often vary through time and space as well. And there's a global need for spatially explicit monitoring and analysis of these, and also quantitatively validated. So we're taking for this PhD an interdisciplinary approach, and the starting point we're looking at is this remote sensing that I am talking about today. So our key research questions for this one is, what is the relationship between the carbon and these variables? Can the spatial variability be actually captured well with remote sensing? And how will it respond to changing environmental pressures at a lagoon scale over long times? So we've had some initial field data work. Here you can see the biomass process for both the salt marsh and for the seagrasses. In the seagrass lab, we have like a friend who was trying to eat the seagrass. I think you can see it here, but the science was not interrupted. So some of the preliminary results can be seen here. At the top, you have the orthophoto, and then the hyperspectral data, where you can see the differentiation between the species quite well, and then the NDVI at the base. However, the results at the moment, we still need to complete more processing before we can get some true definitive conclusions. So at this point, as I know the time is short, I'll move on to conclusions. So open source multispectral satellite remote sensing, which is the focus of the Rio Formosa study, it can be applied to monitor salt marsh shoreline change in coastal management contexts. And for the second study site, remote sensing is confirmed as a salient aspect of the interdisciplinary approach taken in the study, but more testing is required. And I would like to close here. Here's the references. I'd like to say thank you. And also, I would like to dedicate this presentation to my grandfather. Thank you.
Thank you. Thank you very much for your very nice talk and also for the patient to wait until this afternoon. And are there any questions for Tegan, what she's doing or what? Well, you probably had some exchanges with her since yesterday, but she has been an excellent student, of course, but we all know. But she's doing quite well, and very well, I would say, and it's a pleasure to have her back from New Zealand to Italy. So if there are no questions, I also want to mention frappe, because we didn't mention frappe so far, but it's been a nice Wacoma mate. And he did all the mobility, and so good. Thank you very much, Tegan. And the mom of Frappe will speak tomorrow, but still, but we like to mention Frappe. Then it's time for a break. We are on time. We did a very good job also, because everybody took the time, and then also Tegan was very good. And then we have a break, and then we come back for the second part of the afternoon. And thank you very much for your presence here.